You can like
Alright, so good morning, students. My name is Mr. Morioki, and I will be taking you through chemistry. Welcome, everybody. I hope that you have been able to set up Zoom, as we said, because most of these lessons will also be we're also going to be broadcasting them on Zoom as well as WhatsApp. So our lesson today is radioactivity, and we are aware that most of you have not covered this much, and therefore I'm going to start from the very beginning so that we do not disadvantage anyone. Students in schools that have covered the syllabus, as well as those who are still, or rather who are way behind. So for us to understand what radioactivity is all about, I would like us to first of all review a few things you learned in Form 2, and that is about the structure of an atom. In Form 2, you learned that an atom has got two parts. There is the central part that we call the nucleus, that consists or contains protons and neutrons. We also have the outer space here, known as energy levels, where we have electrons. So you have electrons here, and depending on the atom that you're talking about, you could have so many electrons in so many energy levels. Now in radioactivity, we are going to concern ourselves with what happens within the nucleus of the atom, and therefore I'm going to do away with the energy levels. Now, the nucleus of an atom, characterized by its protons and neutrons, is referred to as a nuclide. So for example, if I could use an atom of an element like calcium, if I write something like that and then indicate 20 and 40, where 20 is the atomic number, that is the number of protons, and 40 is the mass number, that is the number of protons plus neutrons. This is the nuclide of an atom of calcium. So in radioactivity, because we're going to be talking about the reactions that take place mostly within the nucleus, we are going to be talking about the changes that occur within the nuclide. Now, the nucleus of an atom, that is a nuclide, contains protons and neutrons, as we have said. The number of protons and neutrons is usually roughly the same. For example, as you can see, in an atom of calcium, we have got 20 protons and we also have 20 neutrons. That is why the atomic number here is equal to the number of protons, that is 20, and the mass number here is 40, which is the number of protons plus neutrons, which makes that 40. That is 20, 20. Now, an atom or a nuclide can either be stable or unstable. A nuclide is stable if the number of protons and the number of neutrons within the nucleus is equal or almost equal. That is to say that if n over p is equal to, that is 20 over 20, if n over p gives you 1, or the ratio of n to p, the ratio of neutrons to protons for that atom is 1:1, then that atom is said to be stable. If the numbers are so different, then the atom becomes unstable, and that is where radioactivity comes in. Radioactivity is the process through which the nuclide of an atom that is unstable disintegrates to give you new particles that are more stable. For example, I will use a nuclide that I'm going to call X. I'm going to call it X. And my nuclide X will have atomic number 120, meaning that we have 120 protons, and the mass number is going to be 160. That means that we have got 120 protons, and then we have got 40 neutrons. If I was to divide N with P, or get the ratio of neutrons to protons, then that number would not be 1, as I said. That would be N over P, that is 40 over 120, that would be 3, no, that is 1 over 3. That is about 0.3333. So it's a very small number. So this nuclide, unlike calcium, the nuclide of X is unstable because the number of protons and neutrons is so different. A ratio of N to P is very different. If you compare that scenario with the case of calcium, then the ratio of N to P is 1, which is a stable nuclide and unstable nuclide. And we could give so many examples of a nuclide that is stable, a nuclide that is unstable. We could compare so many of them, but I believe you understand what you're talking about. So a nuclide that is unstable, like X here, will disintegrate, generating a new particle as well as some energy. It releases some energy. So by definition, radioactivity is the process through which an unstable nuclide disintegrates or splits, forming a new nuclide, and it's accompanied with the release of some energy or radiation. That is radioactivity for you. All right. Now there are two types of radioactivity. We have radioactivity that is natural . So radioactivity can be natural or it can be artificial. Natural radioactivity is the type of radioactivity that happens naturally because the nuclide of the atom that we're talking about is unstable. Artificial radioactivity is radioactivity that is forced or is initiated using some external forces. For example, the nuclide of an atom like the calcium that we had here. We could bombard it or hit it or knock it with fast-moving neutrons to make it to disintegrate. And as I said, in the process of radioactivity, some energy is released or is given off. So it may be necessary for us to cause a nuclide, even one that is stable, to undergo artificial radioactivity so that then we can harness that energy for whatever uses. We have electricity generated from radioactivity. We have atomic bombs, and we have so many other applications. Some of them good, some of them harmful. But it may be important or it may be necessary for you to cause a nuclide to undergo artificial radioactivity. Now, when an atom that was either stable, rather a nuclide, when a nuclide that was either stable or unstable undergoes radioactive or radioactivity, we can also say that the nuclide has undergone radioactive decay. Radioactive. So somebody may tell you that a nuclide of an element X has undergone radioactive decay. That person means that the nuclide has disintegrated or... So this term, radioactive decay, and radioactivity can refer to the same process, or they can be used interchangeably. Now, an element, a nuclide or an atom that is radioactive is an element that naturally undergoes radioactivity. That is, it is radioactive. Most radioactive elements, it has been found, are those that are very huge in terms of atomic numbers, meaning that if I could use my X once again, the number down here is very huge. For the first few elements that you're familiar with, that is chlorine, that is carbon, that is oxygen. For those elements that are within the group of the small atoms, most of them are stable. But as we move on, as the atomic number becomes big, as we get to 100 and whatever other numbers we have up here, as the atom becomes larger, then the atom or the nuclide becomes unstable. So the atoms of the first few elements are mostly stable. But as the atom becomes larger, as the atomic number becomes larger, stability becomes low. I had mentioned that stable nuclides are those nuclides whose ratio of n, the number of neutrons, to p, the number of protons, is roughly 1 to 1. That does not mean that for a nuclide to be stable, then the ratio will have to be 1 to 1. It means that it will be within a range that is close to this. So even an atom that has this ratio being something like 1.4 to 1, or being something like 1.5 to 1, then this atom is still going to be stable. The atoms or the nuclides of elements that are stable are said to be within a range that we normally call the belt of stability or the band of stability. Anything outside that one is unstable. What I mean is, our board is not cooperating with us, but I hope you can see that. And students, if you cannot see what I'm writing, comment that down there. You're able to respond so that we change. If there's a problem, if for example you're not able to see whatever my camera person is recording, you can always say, and it's going to be corrected. So I was saying that if I was to draw a graph of the number of neutrons against the number of protons for different atoms, then I could pick an atom, number 4, whose number of protons is 4, and the number of neutrons is 4, and the number of protons is 4. If I was to pick another one, that is 8 and 8. I could pick another one, 12 and 12. And so on and so forth. So with this graph, you can place the different elements that you have learned, or the first 20 elements that you are familiar with. So anything that is within this line or along that line has a ratio of n to p of 1. Because if I picked an element like this one, whose number of neutrons is 12, I would find that the number of protons is the same. I'm not using a scale here, that's why my graph may not be very nice. So the number of neutrons is 12, and the number of protons is 12 as well. So if you divided 12 by 12, you should get 1. Or if you found the ratio of n to p, then you should get 1:1. So it has been found, after so many years of experimentation and research, that most elements that are stable are usually found within this pad here. That region there. And this is what is called the belt of stability or band of stability. Belt of stability. So any element that falls within this one, this region here, then that element will be a stable element. All right. Let's move on to something else. Let's move on to something else. And we had said that there are two types of radioactivity. We have got two types of radioactivity. There is natural radioactivity, and there is also artificial radioactivity. Now, in both of those two types of radioactivity, I said that the nuclide that was unstable will disintegrate into two different particles or even more, and it will also release some energy or some radiation. So at this point I want us to discuss the different types of radiation. The different types of radiation that are released when an unstable nuclide undergoes radioactive decay. And we have got three types that we're going to concern ourselves with at this level. We have got alpha radiation. I believe that most of us are familiar with this term alpha. It is a Greek letter, so that is alpha. Sometimes it will be denoted using that Greek letter, alpha, radiation. We also have another type, a second type, known as beta radiation. And this sometimes is also denoted using a Greek letter, beta radiation. And the third type is called gamma. Denoted using this Greek letter, gamma. I know that all of us are familiar with those three different Greek letters. So these are the different types of radiation that we're going to concern ourselves with, or we're going to study in this course. Now, alpha radiation is a stream of alpha particles. An alpha particle is a nuclide of helium. All of us from Form 2 are familiar with helium, and we know that helium will have atomic number 2 and mass number 4 and a charge of positive 2 in this case. So alpha radiation consists of a stream of alpha particles which are ions of helium. Beta radiation consists of a stream of electrons, and of course we all know that electrons have a negative charge, so we're going to have these on here. Let's separate these ones. It will be a stream of electrons, and we know that electrons carry a negative charge, so that the atomic number will be 0 here. The atomic number here will be -1, because we know that when I denote a nuclide this way, the number down here is the number of protons, and we know that this is just an electron. So there is no, or we have no protons, and therefore that is going to be a -1, meaning that we don't have any protons. In fact, what we have is an electron which negates the one proton that we would otherwise have. And the number up here is the number of protons plus the number of neutrons, and of course we have none, and therefore beta radiation will be denoted as an electron with a negative down here, a -1, and a 0 here. And then of course we have gamma radiation, and gamma radiation is a wave. The first two here consist of particles, that is helium ions, electrons for the second one, and gamma radiation. I hope that we can note, or we can see, that the first type of radiation here consists of positively charged particles. The second ones here are negatively charged, and the third one has no charge, because these ones are particles, and particles can carry a charge. These ones are waves. It is energy, it is radiation, and therefore it has no charge. It is just a stream of waves, some energy that can be propagated through space. As we, for example, just like light waves, sound waves, yeah, etc. So they carry no charge because they are simply waves. They are not particles. All right. Let us discuss the properties of these different types of radiation. And I think we are going to clear the board so that I use the same space to show the properties. So the best way for us to outline the properties of radiation is for me to compare them. So I'm going to divide my board into 3 sections. and then we can compare the three different types of radiation. So I'm going to compare the three different types. And the first one, as we said, is going to be alpha radiation. The second one is going to be beta radiation. And the third one is gamma. Right. So let's see whether this one serves us any better. All right, that's good. Thank you. So the first type of radiation, which is alpha radiation, we have said consists of ions of helium and they are positively charged. So alpha radiation carries some charge. It is positively charged. So alpha radiation will consist of a stream of particles that carry a positive charge. We have said that these ones will be helium. So remember that. Beta radiation, we have said, consists of a stream of electrons. So this one will be negatively charged. And this is electrons. Like that. And then gamma radiation, we have said, it consists of, it's just a wave that is electromagnetic waves. And therefore, because there are no particles there, gamma radiation does not have a charge, and therefore this is going to be zero or not charged, no charge. Like that. It consists of waves. Property number 2 is what we call ionizing effect. Or before we get to property number 2, we have said that these are helium particles which are positive, these are electrons which are negative, and the third group of, or rather the third type of radiation is gamma with no charge. That means that if we were to pass these three different types of radiation through magnetic or through a magnetic field, then this one would be affected by the magnetic field, this one would be affected by the magnetic field, but this one would not be affected. Meaning that if you passed through, if you passed a stream of alpha particles through a field where we have a positive plate and we have a negative plate, and then your radiation is passing in between here, then these positive particles will be deflected towards the negative side, because we know that unlikes attract and likes repel. So you'll find that alpha particles will, or rather alpha radiation is affected by a magnetic field. It will be deflected to the negative. This is beta radiation will also be affected because it carries a negative charge. So a stream of beta particles will be noted to deviate towards this side. That is beta. That is alpha. And of course, gamma radiation will pass on undeviated because it has no charge. So in fact, we can include that as property number 2. So this one is affected by a magnetic field. Similarly, this one is affected. And no. Let me not use those ones. So gamma radiation is not affected by a magnetic field because it has no charge. The third property of radiation from radioactivity is what we call the penetrating power. And penetrating power means if you are to release a stream of alpha particles through space, how much would they pass? Would they be able to penetrate a piece of paper, a sheet of paper, a sheet of metal, etc.? And alpha particles are the least penetrative, and they can be stopped even by a sheet of paper, a thin sheet of paper. So among the three, alpha particles are least penetrative. They can be stopped by something very thin, even a sheet of paper. Beta particles are more penetrative than alpha particles, so more penetrative. So if they were moving through space, they would penetrate this sheet of paper that we're talking about in the case of alpha, but they can be stopped by a sheet of aluminium or a foil of aluminium, that is aluminium metal. So beta particle is more penetrative than alpha, or rather beta radiation is more penetrative than alpha radiation. Gamma radiation, on the other hand, is very penetrative. It can pass through a sheet of paper without being stopped. It can pass through the sheet of aluminium or the foil of aluminium without being stopped, but it can be stopped by a thicker obstacle, like a block or a wall made of lead metal. So most. Penetrative. So these particles or this radiation can only be stopped by something thick, like a thick wall or a block or a wall of lead metal, that is lead metal. The fourth property is what we call ionizing power. And as these different types of radiation pass through space, they cause air to ionize. By ionizing, I mean that the atoms in air turn into ions. Meaning that if, for example, we had oxygen or we had hydrogen or whatever other gases we have in air, then as alpha particles are passing through space, they knock or they bombard the particles of oxygen gas, hydrogen gas, nitrogen gas, all those particles, and those particles may lose some of their electrons, forming ions. That is ionizing power. So, alpha particles that are in alpha radiation are very heavy. They are helium, or they are essentially they are ions of helium. This means that, as you can see, the mass number of alpha particles is much higher. It's 4 atomic mass unit. The mass number of electrons is very, very low. From your chemistry in Form 2, the mass of a neutron, the mass of a proton was 1 unit. The mass of an electron was almost 0. 1 over 1840. That is a very small number. So, beta particles, that is electrons, are very light. Gamma radiation has no particles, so it's very light. It's almost, it has no weight, because those are waves, those are radiation or energy, and therefore those ones are the lightest. So in terms of ionizing power, helium has the highest ionizing power because of 2 reasons. Number one, or rather alpha, because of 2 reasons. Number one, alpha particles are heavy, meaning that they move slowly through space. So if my particles or if my radiation was being generated here, if this is where I was generating the 3 different types of radiation, and then they were moving forward, then alpha particles would take a lot of time to cover the space from here to that point. That means that they would be in contact with air for a very long time, and therefore they would cause very many atoms to ionize. Beta particles move faster, and therefore they would be in contact with the air, with the atoms of air in this region for a shorter period of time, and therefore beta radiation causes less, or it would cause less radiation, rather ionization, as compared to alpha. Gamma radiation has no atoms even, and therefore it will move very fast, and the ionizing power will be much, much lower. So this one is high, it has high, or highest. Highest ionizing power. This one is lower ionizing power, and this one is going to have the lowest ionizing power. And I hope that is or we understand the reason as to why that happens. I have also talked about the speed at which those different atoms move. So we could take that as our number 5, or as our property number 5, that alpha particles move at the lowest speed through air or through space. Beta particles move at a faster speed, while gamma rays move at the highest radiation among the three of them. That is property number 5. I hope I'm not forgetting any other property. Let me just check that. Yeah, so those are the 5 properties, and as you can see, once you interpret the radiation in terms of the particles that the radiation carries or consists of, then it's easy for you to pick the properties, and you pick the properties starting from what kind of particle are we talking about here. If it's a helium, very heavy, and therefore you can think of the properties. Very slow, it takes more time in space and or in air, and therefore higher ionizing power, penetrating power. It has a charge and therefore affected by a magnetic field, etc, etc. So for you to pick the properties, it's advisable for you to think of these radiations in terms of what particles does the radiation carry. All right, so that is it about the properties of the different types of radiation, and we can move on. I don't know whether there's any question under the comments. All right. So let's talk about something else. And there's something else that we talk about is the type of reactions that take place when we are talking about radioactivity or radioactive decay. At the beginning I said that in the process of radioactive decay, or when one particle is decaying into other particles, the reason as to why the particle or the nuclide would want to disintegrate is because it is unstable, and therefore it will form 2 or more particles that are more stable, and of course some energy may also be released. If the 2 particles that are formed are not stable as well, they may also disintegrate into others, and that process will continue until we form more stable nuclide, and that would form what we call a radioactive decay series that we'll cover in a short while. Before we get to the series, let's talk about radioactive decay involving just 1 step or 2 steps. The chemistry that you learn in this course allows you only to discuss the first 20 elements of the periodic table. In the course of radioactivity, I will be mentioning some other elements that are not among the 20, so that should not worry you. I will not give you the properties of those elements. We are only going to use them for the purpose of this lesson, and or rather in this topic, and you'll not be required to know a lot about them. All right, let's consider the disintegration or radioactive decay of an element called uranium-92, and the symbol for uranium is U. The symbol is U. My pen is a bit, my marker here is a bit too faint. Let me have a different one. Not any better. All right, that's better. All right. Okay, sorry for that, but we are now good. So uranium, atomic number 92 and mass number 236. We can tell just by looking at this element or this nuclide that it is not stable, because the atomic number is 92, the mass number is 236. That means that we have got 92 protons. And how many neutrons are those? Those are 236 from 92. That is 144 neutrons. So you can see the difference. So the ratio that I was talking about, if you divided N by P, or the ratio of neutrons to protons, is not 1 to 1 as we said, and therefore it will disintegrate. An element or a nuclide like this one that is unstable is known as a radioactive element. If it occurs in form of isotopes, that is elements or atoms that have the same atomic number but different mass numbers, then we call it a radioisotope. So this is a radioactive element. If at all we have got isotopes, as I have said, they will be referred to as radioisotopes. Radioisotopes. So, uranium spontaneously undergoes radioactive decay to form other particles, as we are going to say here. All right. So, if uranium was to undergo, or rather uranium undergoes radioactive decay or radioactivity to form two different particles, two different nuclides, 3 neutrons, and it releases some energy. So this is a nuclear reaction. The reactions that we have been covering most of the times since Form 2 were chemical reactions. Chemical reactions take place within the energy levels. An atom will be losing electrons or gaining electrons. But in this case, we are talking about a nuclear reaction in which the components or the atoms that are found within the nucleus will change. We have an increase in the number of protons, the number of neutrons, depending on the type of element that is being formed or the one that is disintegrating. And something that you must note here is that for your nuclear equation to be correct, then there are between the numbers down here on this side of the reactants and on the other side, just like we normally do with the other equations, the chemical equations, so that if I was to add 56 to 36 to 3 times 0, I should get 92. If that is not the case, then there's a problem with the equation and you would need to correct that. If I was to, on the other side, on the upper side, that is mass numbers, the numbers that I have above here on this side, they should be the same as the sum of all these. So that if I added 141 to 92 to 3 times 1, I should get 236. If that is not the case, then there's a problem. I would either need to balance my work or check whether my mass numbers are correct or whether maybe I'm skipping something. And once you do that, then your equation is going to be correct. So somebody may give you a question of this nature, whereby one of these products or the reagents is probably denoted as X, and then you are required to look for X. So, and then this is A, and this is B. To get B, plus 3 times 0, you subtract that answer from 92. On the other side, to get A, you just need 141 plus 3 times 1. The answer, subtract that from 236 and you'll get your A here. Another question that somebody may give you of this or around these concepts is that they may ask you what type of radiation is generated. For example, we have this element here known as thorium, TH. Undergoing radioactive decay excuse me, thorium undergoing radioactive decay. I hope that is clear enough. The radioactive decay to form another element here, or another nuclide, and we don't know the kind of radiation taking place here. We also don't know the kind of particle that is given off. So I'm going to call this one Y. So the question is, what is Y? What kind of radiation do we have here? And to get Y, we just need to get the numbers on this mass number side. On the reagent side, we add them all. On this side, we only have 232. On the other side, we have 228, and we have X. So to get X, that's going to be 232 minus 228, and this gives me 4. On the lower side, we have 90. On the other side, we have 88. So 88 plus D, 88 plus D should give me 90. So D obviously is going to be 2. D is going to be 2. And as we learned, the particle that has a mass number 4 and an atomic number 2 was helium. So this Y here is therefore that one. And therefore, the type of radiation taking place in my second equation here is alpha radiation, and the particles given off are alpha particles or helium particles. And you can do this for any other type of, or rather for any other equation, and you'll be able to get the unknowns as we have seen right there. So that is it for our lesson today. We're going to pick it up from there the next time. I'm going to post some questions around these concepts in our WhatsApp group, so be sure to check them out. Do as much practice as possible and read ahead of me. In the next lesson, we're going to discuss the the radioactive decay series, and also what are the uses of the energy that we're talking about here. Does it pose any dangers to us? And if there are any dangers, what can be used to minimize those dangers? Bye bye, and see you next time.